Hello, everyone. Today, I'll be discussing the Medical Segmentation Decathlon. The MSD is an international challenge that aims to identify a general-purpose algorithm for medical image segmentation. It provides a collection of datasets with images across 10 different anatomies, including the brain, heart, liver, and more. Participants are tasked with developing algorithms that can independently solve each segmentation task without human interaction. The challenge has shown promising results, pushing the boundaries of medical image analysis. This discussion is particularly relevant and beneficial for individuals involved in medical image analysis, research, and medical engineering students. What is medical image segmentation? Medical image segmentation consists of indicating the surface or volume of a specific anatomical structure in a medical image. Input images can range from X-rays and ultrasonography to CT and MRI scans. A segmentation algorithm will provide an output that indicates a region of interest as context or a label for every pixel or voxel in the image. A very basic example of a voxel-based segmentation algorithm is simple thresholding. This method looks at the intensity of a voxel and compares it to a set threshold. If the voxel is above the value, the algorithm will mark it as part of the structure, while if the voxel is below the value, it will be marked as surroundings. This method, however, only works well for structures that have a very different intensity from their surroundings and are not affected too much by noise. Why medical image analysis is important? In medical image analysis, these algorithms can assist in the detection and diagnosis of various conditions, such as tumors, lesions, anatomical abnormalities, and pathological changes. They can also aid in the evaluation of disease progression, treatment response, and prognosis. Next, modalities of medical images. Medical imaging modalities are various techniques and technologies used to create images of the human body for diagnostic and therapeutic purposes. These modalities differ in the type of energy they use and the kind of images they produce. Here are some common modalities of medical imaging. Computed tomography, magnetic resonance imaging, ultrasound, positron emission tomography, X-ray. Attributes of medical images datasets. The attributes of medical image datasets include the image modality, such as X-ray or MRI, anatomical region, specific body parts or organs, image resolution, level of detail, image format, DICOM or NFTI, and dataset size, number of images or data volume. These attributes vary depending on the dataset and its purpose, with different datasets focusing on specific medical conditions or research objectives. SWOT analysis. In medical imaging, the strength of advanced imaging modalities and computational tools provides healthcare entities with a technological edge. Cutting-edge modalities, exemplified by high-resolution imaging, elevate diagnostic precision. Computational tools, inclusive of artificial intelligence, enhance image analysis, thereby improving patient care and fostering competitiveness. This technological prowess not only supports efficient clinical practices but also fuels research, enabling breakthroughs in medical understanding. However, a weakness lies in the variability of image quality and data annotation standards, hindering seamless collaboration. Standardizing these protocols becomes imperative for reliable diagnostics. Opportunities arise with the integration of machine learning and deep learning for automated segmentation, promising enhanced diagnostic efficiency and novel insights. Yet, ethical and privacy concerns pose threats. Safeguarding medical data integrity is crucial, especially as machine learning relies on extensive datasets. Addressing these concerns is vital to responsibly integrate advanced technologies and maintain public trust in healthcare systems. Pixel-wise classification, also known as semantic segmentation, is a type of image analysis where each pixel in an image is classified into a certain category. This is different from traditional image classification where the entire image is assigned a single label. In pixel-wise classification, every pixel is given a label, resulting in a detailed, pixel-level map of the image. In the context of medical imaging, pixel-wise classification can be extremely useful. For example, it can be used to identify and classify different types of tissues in an MRI scan, or to detect anomalies such as tumors in a CT scan. Each pixel in the image is analyzed and classified, providing a detailed understanding of the image content. For example, consider a case where we are analyzing a CT scan of the lungs. In this case, we might want to classify each pixel as either lung tissue, cancerous tissue, or other. The pixel-wise classification model would take the CT scan as input and output an image of the same size, but where each pixel's intensity corresponds to the class it belongs to. This process involves training a deep learning model, such as a UNet, on a large dataset of CT scans where each pixel has been manually classified. Once the model is trained, it can be used to classify the pixels in new, unseen CT scans. This is particularly relevant in a medical context because it allows for a high level of detail and precision. It can help doctors and medical professionals to make more accurate diagnoses and treatment plans. For instance, in radiology, pixel-wise classification can help to precisely locate and measure the size of a tumor, which is crucial for treatment planning. For example, the infographic above illustrates the process of pixel-wise classification in medical image analysis. This process is often used in the analysis of MRI or CT images. The process begins with the acquisition of the medical image, which is then pre-processed to enhance its features and remove noise. The pre-processed image is then segmented into different regions, each representing a different tissue type or anatomical structure. Each pixel in the segmented image is then classified based on its intensity value and the values of its neighboring pixels. This classification can be done using various machine learning algorithms, such as decision trees, support vector machines, or deep learning models. The result is a classified image where each pixel is assigned to a specific class, such as tumor, healthy tissue, or blood vessel. This pixel-wise classification allows for a detailed analysis of the medical image and can aid in the diagnosis and treatment planning of various medical conditions. Similarities between MRI and CT scan datasets. MRI and CT scan datasets are similar in several ways. 1. Data structure. Both MRI and CT scan datasets are typically structured as 3D volumes, where each volume is composed of a stack of 2D images. Each slice represents a thin section of the body. 2. Grayscale images. The images in both datasets are grayscale. The intensity of each pixel corresponds to different tissue types. 3. Use in medical diagnosis. Both MRI and CT scans are used in medical imaging to diagnose and monitor various health conditions. They can be used to image any part of the body. 4. Image analysis. Techniques used for analyzing MRI and CT scan images are often similar. These include segmentation, registration, and feature extraction. However, it's important to note that while they are similar, MRI and CT scans also have significant differences. MRI uses magnetic fields and radio waves to generate images, while CT scans use X-rays. As a result, they have different strengths and weaknesses in terms of what they can image effectively. Strengths and weaknesses of MRI and CT scan datasets. MRI and CT scan datasets have distinct strengths and weaknesses. MRI excels in imaging soft tissues and organs without using radiation, making it safe for patients. However, MRI scans are time-consuming and more expensive than CT scans. Additionally, MRI cannot be used with certain metal implants. On the other hand, CT scans are faster, less expensive, and provide detailed images of bones. However, CT scans use ionizing radiation, which can be harmful, and they do not provide as much detail as MRI for soft tissue imaging. Understanding these strengths and weaknesses helps in choosing the appropriate imaging modality based on the clinical requirements. Deep learning approaches for medical segmentation. What a UNet is and its relevance to medical segmentation. UNet is a type of convolutional neural network that was specifically developed for biomedical image segmentation. It was first introduced by Ronneberger et al. In their 2015 paper titled, UNet, Convolutional Networks for Biomedical Image Segmentation. The UNet architecture is characterized by its U-shaped structure. It consists of two parts, the contracting path and the expansive path. 1. Contracting path. This part of the network captures the context in the image. It consists of convolutional layers, each followed by a rectified linear unit and a max pooling operation. 2. Expansive path. This part of the network enables precise localization using transposed convolutions. Here, the feature map from the contracting path is upsampled and concatenated with a cropped version of the feature map from the contracting path. The final layer of the U-net is a 1-by-1 convolution used to map each 64-component feature vector to the desired number of classes. How it works in medical segmentation. U-net is particularly relevant to medical image segmentation due to its ability to produce high-quality segmentation results even with very few training images. It does this by using extensive data augmentation and a special loss function for training, which makes it very effective for tasks like tumor detection, organ segmentation, and vessel segmentation in medical imaging. Evaluation metrics for medical segmentation. Evaluation metrics are used to quantify the performance of the segmentation. Some of the common metrics used in medical image segmentation are: here's an introduction to some key evaluation metrics, including the Dice Similarity Coefficient, DSC, Jacquard Index, sensitivity, specificity, and accuracy. I am explained one of this evaluation matrix with example. The Dice Similarity Coefficient, DSC, also known as the Svensson Dice Coefficient, is a statistical tool that measures the similarity between two samples. In the context of medical image segmentation, these two samples are typically the ground truth and the predicted segmentation. The DSC is defined as twice the area of overlap between the predicted and ground truth divided by the total number of pixels in both images. Mathematically, it can be represented as DSC equals 2 asterisk, prediction asterisk ground truth, / prediction plus ground truth. The value of DSC ranges from 0 to 1. A DSC of 1 indicates perfect agreement between the predicted and ground truth segmentations, while a DSC of 0 indicates no overlap. For example, consider a case where we are segmenting a tumor from an MRI image. The ground truth is the manual segmentation done by a radiologist, and the predicted segmentation is done by our model. If the area of overlap between the predicted and ground truth segmentations is 50 pixels, the total area of the predicted segmentation is 100 pixels, and the total area of the ground truth segmentation is 100 pixels, then the DSC would be DSC equals 0.5. This means that 50% of the predicted segmentation overlaps with the ground truth, indicating a moderate level of agreement. This video on the Medical Segmentation Decathlon benefit healthcare professionals, researchers, medical imaging specialists, and medical engineering students. They provide valuable insights into medical image segmentation, fostering knowledge, collaboration, and advancements in the field. Thank you so much for watching this video.